Okay, so let's continue the part concerning estimation. And now, okay, in this video, I want to answer the following question. Is the maximum likelihood estimator optimal or not in the sense of the mean square error criteria? Okay, and you are going to see that this problem will be linked to what we call the Cramer-Rao lower bound, in fact. Okay, so we have this. Okay, so before to pass to the definition of the Fisher information, that is the keystone of the Cramer-Rao lower bound. Okay, I just want to continue with two little examples. Okay, in relation with finding the maximum likelihood estimator. Okay, so let's take this example here. So another example. So we are going to do one in the discrete, okay, and one also again in relation with the Gaussian distribution. So here, suppose that your random variable of interest, okay, follows a Poisson distribution of parameter lambda 0, okay, lambda 0 belonging to R plus star. You don't know lambda 0, okay, but you have an n sample of x, okay, and your hypothesis is that, okay, you know that you are in the framework of the Poisson distribution, okay, that is, we know that the probability that x is equal to small x if the parameter is lambda, okay, is given by the probability mass function for x belonging to n, is given by the probability mass function of a Poisson, that is, okay, the classical formula, exponential minus lambda, lambda to the power x over x factorial with my small x here that belongs to n, okay? So I want to find the maximum likelihood estimator of lambda 0, okay? So to do this, I have to compute the log likelihood, okay? That is just in this situation, the sum from I equal to 1 to n of the logarithm of the probability mass function. So I can write it this way, capital X equal to xi lambda. Okay, it's the log likelihood that I will be able to compute using this one. And if I replace inside, I will have what? Y equal to 1 to n. So the logarithm of what? So I have minus lambda, okay, plus xi, the logarithm of lambda, minus the logarithm of xi factorial. So something that I can write in a better way as minus n lambda. I have the sum of the xi here that I can express as logarithm of lambda capital N x capital N over line. So excuse me, just, okay, just, excuse me, I have forgotten to, so let me just do, okay, so sorry for this little small break, okay, just because I have forgotten to split my screen, okay, so let's do this and I will explain again what I have done. Okay, so I have to split my screen and then I obtain what I have done here. So what I have done, my idea is to start from x that follows the Poisson of parameter lambda 0. It's exactly what I have said. I have my n sample, okay, of this distribution. And I know, so keep in mind that lambda 0 is unknown, okay, and I have this family of probability mass function related to my problem. I know that they are Poisson, but I don't know the value of the parameter lambda 0, okay? If I want to find the maximum likelihood estimator of my unknown parameter here, I have to compute the log likelihood. The log likelihood, that is, in this case, the sum of the logarithm of the probability mass function taking at the point xi. Okay, so this quantity may be computed from this one here, and I obtain, plugging inside, okay, xi, I obtain this one, and I can write it, okay, just this way, minus n capital lambda coming from this term here, because I have n term inside the sum, and here a constant. Then for this one, I have the sum of the xi that I can express as capital M multiplied by xn over line, the sample mean, okay, and minus, here, minus, I can write it this way, the sum from I equal to 1 to capital M of the logarithm of xi factorial, okay? I don't need to handle this term because, as you know, in order to find the maximum likelihood estimator, you have to compute or to solve the Euler condition, that is first to compute the derivative with respect to lambda. If I do this, I obtain what? I obtain minus n plus, okay, the derivative of lambda, that will be 1 over lambda, the derivative of the logarithm of lambda, that will be 1 over lambda, and I obtain n xn over line over lambda and 0, because here I have something that is independent of lambda. And if I solve this one, if I solve this one to be equal to 0, I obtain, okay, as the maximum likelihood estimator here, but the one that solve this one equal to 0, this one equal to 0, and so I obtain here simply xn over line, okay, and I know that this one, so I have here the maximum likelihood estimator, that is in situation simply the sample mean, with an expectation of xn over line that is equal to lambda 0 from what I know about the sample mean, and I know that the mean square error in this case is just equal to the variance, and I know it, okay, that is just lambda 0 here over n, because I know that the variance of a Poisson is simply lambda 0. Okay, so my first example here is in the discrete case, and I am interested in finding the maximum likelihood estimator related to the parameter of my Poisson. I obtain exactly the sample mean here. So let's take another example, example 2. I have already done an example in the case of a Gaussian distribution with 2 parameters, mu and sigma square. And here, okay, we are going to suppose the following. So here you suppose that x follows the n mu 1. Why not mu 0, let's say. Okay, so I know the variance, and I suppose it to be 1 here, but it can be, okay, any kind of known variance, but I take it equal to 1. Why not here? And the only parameter I don't know in this case is the mean, that is mu 0. Okay, so I have my n sample here. And the only thing I know is that, okay, the density of x given my parameter mu here is equal to 1 over the square root of 2 pi, because sigma square is equal to 1 exponential minus x square, excuse me, because I have a mean, so it will be x minus mu square over 2. Okay, so this is, I know what is the family of my distribution. It's a Gaussian distribution with a mean that is unknown and a variance equal to 1 here. I know it. Okay, so it's known variance in this case, known variance. It's not the case in general, but here I suppose it. I have a known variance. Once again, if I want to compute the log likelihood, it's the sum from I equal to 1 to n of the logarithm of f of xi mu, And I obtain in this case, it's a computation that I have almost already done. Okay, it's the sum from I equal to 1 to n, okay, of minus 1/2 the logarithm of 2 pi minus xi minus mu square over 2. Okay, it's the log likelihood. So I have this, so excuse me, I have written here lambda, it's not lambda, it's mu, that I obtain this way. Okay, so if I want to find the maximum likelihood estimator, I have to compute the score, that is just the derivative of the log likelihood here. So this term disappears because I don't have mu inside, okay, and then I have this one here that is simply, okay, so when I compute the derivative of this one, it's the sum from I equal to 1 to n, okay. So I obtain simply xe minus mu, okay. That's all, because I have simplification between the two when I compute the derivative of the square here. So I have this one, and so if I want to find the maximum likelihood estimator in this situation, I have to solve the Euler condition that will give me, okay, the mu at equal to 1. So it is the one that solves this equation. And once again here, I obtain the sample mean. Okay, I obtain the sample mean, and I know that the expectation of mu at here is equal to my parameter of interest, mu 0, and that the variance here of mu at in this particular situation is the variance of my sample here, that is simply equal to 1 over n. Okay, so this is, excuse me, this is what I can obtain in the case of computing the maximum likelihood, okay, of a Gaussian sampling with a known variance. I obtain once again the sample mean. Yeah, okay, as in the previous case of the Poisson. So you have here an example in the discrete case, and now an example in the continuous case. And my question, the question I want to solve in particular for the two last example is, are the maximum likelihood estimator I have obtained optimal? So I know that they are unbiased. Okay, so if I want to check if they are optimal, okay, I just need to check if they have a minimal, in fact, a minimal variance. Okay. So a priori, it's complicated to do this because I have to compare, okay, their variance with the one of all the unbiased estimators. So if I want to do this, okay, it will be really complicated because I don't have an exhaustive description of all the unbiased estimator. But fortunately, okay, we are going to have, okay, an interesting inequality that is the Cramer-Rao inequality, that is an inequality that will give you the lower bound for the mean square error of unbiased estimator. A lower bound for the mean square error of unbiased estimator. And typically, okay, if you reach the lower bound, okay, but you will be sure that you will be optimal because you have a lower bound for the mean square error. If you mean square error is exactly this lower bound, you can't be below. So you will be optimal in the sense that you will be BU. Okay. So in order to define the Cramer-Rao inequality, I need to define what is called the Fisher information. Okay. So first, we are going to see the definition in the case where theta, my parameter of interest, is a real number that is in dimension 1. So it's exactly what we are going to do here. I suppose theta, okay, to be included in R. Okay, I am in the scalar case. Okay, theta is a number. So it means in particular that if I want to compute in this situation the maximum likelihood estimator, I have a single Euler condition to check, okay, the one related to the derivative with respect to theta. I don't have a gradient, okay, or a very particular gradient with a single component. Okay, so let's have a look on the definition of the Fisher information in this situation. Okay, so we are, I repeat, in the case where theta is just a number. Theta is a number. Okay, so I defined the information, the Fisher information at the point theta 0 here as the variance of the derivative of the log likelihood at the point theta 0. And I remind you that the derivative of the log likelihood is just what I have called the score. Okay, so it's the variance of the score at theta 0. And I said, so in fact, you have two equivalent definitions, that this variance is just the expectation of the square. So at this stage here, okay, I have a little thing to say is that, okay, I define, why not, my I of theta 0 as the variance of the score at the point theta 0 here. Okay, and I said, and for the moment, I don't know why I have this, okay, that the variance in general, you know the definition of the variance, that is the expectation of x squared minus the expectation of x squared. Okay, but here in this particular situation, I have a single term here that is just the expectation of the score square. So I want to prove this here, okay? So why I have this? So first question, okay, why I have this thing here? So why I have this thing? But because of the following. So it's something that I have already done, okay, but let's do it again, okay? So let's have a look on, okay, what I know. I know that, okay, I know that the expectation of the log likelihood at the point theta here is equal to what? So the expectation of the log likelihood at the point theta is equal to the sum, okay, from I equal to 1 to n of the expectation of the logarithm of x of xi theta, by definition of what is the log likelihood. If I am interested in such a term here, okay, this one, what I obtain here by this one, so expectation of the logarithm of f of xi theta is equal to the integral minus infinity plus infinity of the logarithm of f of x theta multiplied by the true density function, that is the one of xi, that I don't know, but I can denote this way, x theta 0, where theta 0 is the true parameter here. I have this one, okay? And from this one, it's a computation that I have already done, is that if I compute the derivative of the previous quantity with respect to theta, I have the derivative of this integral, and I have said in the first part of the video that when I compute the derivative of the integral, it's just the integral of the derivative. So I have to compute the derivative of this term here. So it's integral minus infinity plus infinity of the derivative of the logarithm here with respect to theta, and I obtain logarithm of u being differentiable and its value being u prime over u. I obtain d over d of theta, f of x theta over f of x theta, f of x theta 0. It's something that I have already done, but I do it again, okay, to make it clearer maybe. So I continue. So I obtain this one, okay? I obtain this one, and in particular, I obtain that my quantity of interest here, so d over d theta of, oh, I can write it this way. So excuse me, I will write it this way. So if I have this, with this one with the derivative that is given by this expression, if I compute the expectation, so the derivative with respect to theta of the expectation of the log likelihood is simply equal to the expectation of the derivative. Okay, that's what I have supposed. And so I can write it using what I have done here. It will be the sum from I equal to 1 to n of the derivative of these quantities that I have computed this way. So I have here minus infinity plus infinity d over d theta f x theta over f x theta f x theta 0 dx. Okay, so I have this one obtained from this computation in green here. So let's duplicate. So I have this one. So let's erase what I have done previously here, this one. Keep in mind what I want to do. I want to prove that the variance of this quantity is equal just to the expectation of the square, in some sense that I want to prove that the expectation of this quantity is 0. It's exactly what I will do here. Okay, so from this one, what I can deduce from this one? I can deduce from this one that, okay, the expectation of d over d theta ln of theta 0 here, I plug theta 0 inside now, not theta. I have theta here, I plug theta 0, I obtain what? So if I plug theta 0 in this expression, I will have simplification between this term and this term. So if I plug theta 0 in my expression here, I obtain the sum from I equal to 1 to n, integral minus infinity plus infinity of what? Of d over d theta f of x theta 0 dx. I have this one, okay, from the fact that these two terms, this term and this term simplify when theta is equal to theta 0. And what is this one? So in fact, I have already done this computation, okay. I remind that it is equal to 0. Why? Because of this argument here, I have already used. I know that I have density functions. So this one is equal to 1. And if I compute the derivative of this expression, I obtain this. And so this relation for any theta, if I take it for theta 0, I also obtain 0. And so you have what you want, that is this expectation here, this expectation is equal to 0. And so the variance is equal to the expectation of the square. Okay, so what I have done here is just to prove that this equality here is true. In order to compute my variance here, I have simply to compute the expectation of the square. Okay, so this is the definition of the Fisher information. Fisher information is defined as the expectation of the square of the score function, that is the expectation of the square of the derivative of the log likelihood at the point of interest, that is here theta 0. Okay, So I have the expectation of a square to compute with a log likelihood, okay, that is a sum. That is a sum. So I have, okay, the expectation of the square of a sum to compute, something that is sometimes a little bit complicated to do. But thanks to the proposition B2, we are going to see that, in fact, the computation of Fisher information may be easier and easier because, okay, we are going to prove that, in fact, it's a computation I have already done, but we are going to do it again, okay, that if I compute, okay, so the Fisher information defined, as we have proved just before, as the expectation of the square of the score, that is the derivative of the log likelihood with respect to the parameter of interest, is in fact none other than minus the expectation of the second derivative of the log likelihood. And this one is more and more flexible to handle because if you want to compute it, what you will have to do, compute the log likelihood, compute the second derivative, and then just compute an expectation of something that will be in general easier to compute than the expectation of a sum of a square as defined in this expression. Okay, so what I will do now is to do the proof of this proposition here. You are going to see that the idea will be the same thing. Okay, so I am interested in, so it's proof of proposition B2. So I am interested in this quantity here. Okay, I am interested in this quantity. In particular, I am interested in the expectation of this second derivative. Okay, but I know from what I have done before is that, okay, this is what? This is just here, okay, the second derivative is just the derivative of the first derivative. Okay, so let's do the computation here. So it's the expectation of the derivative with respect to theta of something here that I can express this way, the sum from I equal to 1 to n, okay, of what? So the derivative of the log likelihood, that is just d over d theta f xi theta over f of xi theta. Okay, it's the derivative here, the derivative of the logarithm of f xi theta as the expression of the log likelihood imposed. And now, okay, I have this derivative of this one to compute. So I will obtain the derivative of a ratio, that is sum from I equal to 1 to n of the derivative of this one, that is the second derivative with respect to theta of f of xi theta multiplied by this one minus d over d theta f xi theta multiplied by the derivative of this one, that is exactly this one. So I can put a square here. And over what? Over f of xi theta square. So I have this one here. Okay, so the expectation of the second derivative of the log likelihood, okay, is given by this expression. Okay. So what we are going to have a look on here, the idea is to see what happened for this quantity here. So let's write it. So I can write it in this form. So it will be the sum from I equal to 1 to n. So I can express the expectation as an integral, and I will have two terms. So integral minus infinity plus infinity, d2 over d theta square, write it this way, f of x theta multiplied by f of x theta over f x theta square multiplied by the density, the true density, that is fx theta 0 dx. Okay, so this is this expression here, the expectation of this term here. This term, they obtain. The expectation of this term is given by this expression in blue here. And then, so how to do here? I want to continue my computation, and I will have here, so the quantity in green here, that will give me what? So I continue here, in fact. Okay, so I will have minus the integral minus infinity plus infinity of d over d theta f of x theta square divided by f x theta square and multiplied by the true density, that is fx theta 0 dx. Okay, so I obtain the expectation of the second derivative this way. Okay, so I am here. Let's duplicate this slide. Okay, tuk. Write this. Okay, I have obtained this quantity here. So just keep in mind that what I have computed here is just what I have computed here is just here the expectation of the second derivative of the log likelihood. So this quantity is equal to this one. Okay, so I have this one that implies the following. What is this quantity if instead of theta, I have theta 0? So I am interested in this quantity here. Okay, so it's not the same thing because you have here theta 0 instead of theta. And if I do this, I will have some simplification. So for this one, okay, so if you have here fx theta 0, if I put theta 0, you have fx theta 0 squared, that will simplify with this one. So you have a first term that is the sum from I equal to 1 to n, integral minus infinity plus infinity, second derivative with respect to theta of fx theta 0 dx. So it is this first expression here. And then I will have minus the sum from I equal to 1 to n of integral minus infinity plus infinity. So here, if I plug inside theta 0, I have a little simplification here. I have d over d theta f x here, theta 0 square over what? Over f of x theta 0 dx. I have this, okay? And I have to handle once again a little this one, okay? So I duplicate once again. So I obtain this. So the quantity I have computed now is this one. I have two parts. I have the part in red and the part in green. Keep in mind that For the part in red here, for this one, so for the part in red here, keep in mind that I have the following. We have already seen, it's an argument that I have already used previously. This is equal to 1 because it's the integral of a density. If I compute the derivative, supposing that I can invert between integral and derivative, I obtain this one equal to 0. And if I compute the second derivative, I obtain, of course, once again 0 because I compute the derivative of something that is already null. So this one is 0. And so this term here is equal to 0 from this computation here. From this computation, this term is equal to 0. For the second one here, this one, the one in green. What is this one? I said just that the integral minus infinity and plus infinity of d over d theta f of x theta 0 square over f of x theta 0. What can I do here? I can express it as an expectation, in fact. So if I want to express it as an expectation, okay, so I am interested in this term here. So this term I have here, okay. So let's write it this way. I am interested in this term. I want to express it as an expectation. So what I do, I multiply by the density of the xi and I divide by it in order to equalize the thing. And if I do this, I obtain this one as, okay, as what? As the expectation of the derivative with respect to theta of the logarithm of f of xi theta 0, and I put a square here. So this quantity, that is my quantity of interest here, may be expressed this way. And why I do this? What I multiply and divide the density in order to make appear a derivative. And I have here, I just say the expectation of the derivative of the log square because I obtain u prime over u square. That is exactly this term here. U prime square over u square. That is exactly this quantity of interest. So once again, if I duplicate in order to conclude, I have obtained what? So if I summarize what I have obtained here, so this term in red is equal to 0, so I can erase it. I can erase the computation in order to justify. And here, if I continue my computation here, this is equal to what? I can use this. I can use this in order to obtain minus, so this one implies this, minus the sum from I equal to 1 to n, okay, of what? Okay. The sum from I equal to n. Okay, so just let me have a look 1 second. Okay, so it's this quantity that I am interested in. Okay, so I have this one that is just, okay, but I copy what I have found here. The expectation of d over d theta, okay, the logarithm of f of xi at the point theta 0 square. And that is exactly what I want. That is, okay, in order to conclude that I of theta 0, okay, that is defined this way. So here you have in green here, you have minus the expectation of the ln of theta 0 over d of theta square. And so my quantity of interest, that is the expectation of the second derivative of the log likelihood here at theta 0, is given by minus the expectation of the square of the score, in fact, the derivative of the log likelihood with respect to theta at the point theta 0. And here you see that this definition from the definition B5 is what? But it is simply equal to minus I of theta 0, minus I of theta 0. And so I have proved my result. That is the Fisher information that is defined a priori this way as the expectation of the square of the derivative of the log likelihood with respect to the parameter of interest at the point theta 0 that can be obtained in an easier way as minus the expectation of the second derivative of the log likelihood at the point theta 0. Okay? So I have this. So I have proved the proposition B2, and of course, okay, I have done the proof here, but you can omit it if you want, okay, first vision of this session. And of course, and this proof won't be at the program of the final exam, but it was just to show you that, okay, I have this proposition B2. Okay, so maybe let's do some little computations. What I have here, so it's this one, yes. So let's do this. Let's come back to the two first examples, okay, I have done at the beginning of this little video here. Okay, so in the case where x follows a Poisson of parameter lambda 0. So if you have a look on what I have done, so in this situation, where is it? Maybe this one here. So in this situation where x follows a Poisson of parameter lambda 0, I have obtained this for the log likelihood and this one for the derivative of the log likelihood. Okay, so keep this in mind. I have this one for the derivative of the log likelihood. So let's write it. Okay, so I have what? I have d of ln of lambda over d of lambda. Okay, in this situation, that is equal to what? That is simply equal, okay, to what I have obtained here. So let's come back because I have forgotten what I have obtained. Minus n plus n xn over line over lambda. Minus n plus n xn over line over lambda. Okay? So if I want to compute the Fisher information in this situation, okay, what I have to do, I have to compute the second derivative. So from this one, I can deduce that the second derivative of the log likelihood with respect to lambda, it's very easy to compute. It is minus n xn over line over lambda square. Okay? And so if I want to compute I of theta 0 in this case, what is I of theta 0 in this case? Okay, it is just minus the expectation of this quantity. So it is expectation of n xn over line over, okay, lambda 0 square, that is n over lambda 0 square. And what is the expectation of the sample mean? Here, we have already seen that the sample mean is unbiased here, so I obtain lambda 0. And so I have here n over lambda 0 in this situation. Okay, so in this case here, if I take the other case we have done together, this one, the case where x follows the n mu 0, 1. Okay, so I have obtained what? I have obtained a log likelihood, the derivative of the log likelihood that was obtained this way here. Okay, so the derivative of the log likelihood in this situation is what? So let's have a look. The sum of xi minus mu. So I obtain this. Okay, if I compute the second derivative, it's mu here. I obtain what? So here I don't have mu, so it remains, okay, minus 1 with the sum here, so it is minus n. So the Fisher information in this case here is simply n in this situation. And in this situation here, I have this one. So you have a concrete example of such a computation in the case here of a discrete situation with a Poisson, and in a second situation that is related to Gaussian with non-variance. Okay. And what is the interest of this Fisher information? The interest of this Fisher information is that, okay, it allows us to have the following very important result in statistics that is called, okay, so it's not this one that I will remove this one. Okay, and I have here what we call the Cramer-Rao lower bound, okay, that is given by this inequality. So what is this inequality? So just let me have a look on. So, okay, I have this one, so I will just duplicate several times this, okay, and I have this quantity. Tell you the following. So suppose that you have a parameter of interest, theta 0, that you want to approximate, okay? This Cramer-Rao lower bound tell you that if you have an unbiased estimator of this parameter based on capital N observation, then the mean square error that is equal to the variance is always greater than the inverse of the Fisher information. So I repeat, the mean square error is in this case always greater than the inverse of the Fisher information. In the sense that if this theorem is true, once the variance is equal to the lower bound, we are sure that the estimator is the best unbiased estimator. So you have here an inequality that will allow you to check if one estimator is the best or not with respect to all unbiased estimators. So it means that you won't have to compare all the estimators between them, doing pairwise comparison, computing mean square error. If you are sure that you reach the lower bound, you are sure that you are best unbiased estimator. Okay? So just have a look on what I have done previously here in my two little examples. In this case, okay, I have found these two Fisher information. Okay, so let's write just in my examples before to do the proof of this one. Okay, what happened here? So in the case of my examples, I have the case where X follows the Poisson of parameter lambda 0, and I obtain for I of lambda 0, I have obtained what? It was not theta 0, it's lambda 0 here. Lambda 0 here, whatever. I obtain this one. So I obtain n over lambda 0, implying that I lambda 0 minus 1, that is the lower bound for the mean square error of an unbiased estimator, is just lambda 0 over n. But I have obtained the maximum likelihood in this situation. The maximum likelihood was the sample mean. And if I compute the variance of the sample mean, and I know that the sample mean is an unbiased estimator, okay? So the sample mean is an unbiased estimator here. And its variance classically is equal to lambda 0, not over n0, but over n. That is equal to the Cramer-Rao lower bound, in fact. And I can deduce from this that xn over line is bu in this situation. So if you approximate the parameter of a Poisson distribution of parameter lambda by the maximum likelihood estimator that is in this situation equal to the sample mean from the Cramer-Rao lower bound, okay, the variance that is the mean square error of this estimator is equal to the inverse of the Fisher information, and so xn over line is bu. Let's see the other example. If x follows the n mu 0, 1, we have seen that in this situation, I of mu 0 was equal to what? It was simply n, implying that the lower bound in the Cramer-Rao inequality is equal to 1 over n. In order to approximate mu 0, we have also obtained as a maximum likelihood estimator the sample mean that is unbiased and with variance that is in situation just equal to the variance of each observation, that is 1 here, over the number of observation that is in fact here the inverse. And so once again, xn over line is the best unbiased estimator. Yeah. Okay, so we see that in our two little examples in dimension 1, okay, in our two little examples in dimension 1, then what we obtain are two bu estimators, okay, because they reach the Cramer-Rao lower bound, and here they are the sample, simply the sample mean here. And in fact, this result is not that surprising because it's something that is more general. So keep in mind that now I have a criteria in order to check if someone is a bu or not. If I reach the Cramer-Rao lower bound, I am sure that I have a bu. If I reach the Cramer-Rao lower bound, I'm sure that I have a best unbiased estimator in this situation. And you have a theorem that I will admit in this course that tell me that if you have a bu, if a best unbiased estimator exists, necessarily it will be the maximum likelihood estimator. So this second result is also very important because it tells you that maximum likelihood estimators, in fact, are really, really important, because if there exists a bu, it will be necessarily the maximum likelihood estimator. Okay, so I have this one. So maybe I will do the proof of this theorem. Okay, you can drop it if you want, okay, in the first vision of this session. Okay, I won't include the proof in the program of the final exam. Okay, but I do it because it's a nice application of the Cramer, of the Cauchy-Schwarz inequality here. So let's do the proof of this result. Okay, so I admit B2, but for B1, so let's do the proof of B1. Okay, so T, okay, I will denote by T of x1 xn here. Okay, I know that I have an unbiased estimator, so I know that the expectation of t is equal to, by my parameter of interest, that is theta 0. Okay, in particular, if I compute the derivative of this expectation with respect to theta 0, I obtain simply 1. Okay, so when I compute this quantity here, t is a function of x1 xn, so I can write it as the derivative with respect to d of t theta 0 of what? So I have a multiple integral because I know that here, okay, what is the joint density? The joint density here, because of the fact that I have independence, this joint density is simply equal to the product of xi theta 0 I equal to 1 to capital N, because I have here the n sample that are independent random variable having as a true density this one here. So when I compute the expectation here, it will be just the multiple integral. Okay, I have n integrals here, this way, of what? Of t of x1 xn. Okay, and then the product f of xi theta 0 I equal to 1 to n dx1 dx. Okay, I have this one here. Okay, and I know that here, okay, you have the product of the density function at the point xi, okay, and at the true parameter theta 0. Okay, so I have this. Okay, so I have this multiple integral here. So what is this one? Okay, so I remark that it is the exponential of the logarithm of this quantity. So the exponential of the sum from I equal to 1 to n of the logarithm of f of xi theta 0, this one. Okay, so if I suppose that I can invert derivative and integrals, as I have always supposed here, I obtain for this one, so a multiple integral of what? T x1 xn, and the derivative of this one with respect to theta 0, that will be just the sum from I equal to 1 to n of the derivative with respect to theta of the logarithm of f of xi theta 0. So it's a theta 0 here. Okay, and time what? But the exponential of the sum from I equal to 1 to n of the logarithm of xi theta 0 that I integrate with respect to my n variables here. Okay, so I write nothing instead the fact that I invert between the derivative of the integral and the fact that I have the derivative of an exponential. So if you want derivative of exponential u, that is u prime multiplied by u. Okay, you have u prime here. But here you have a multiple integral with respect to what? Here you have, in fact, the density, the joint density of x1 xn here, the joint density of x1 xn, and in fact I can express this multiple integral as an expectation. It's just the expectation of what? Of t of x1 xn, okay, of what? The sum from I equal to 1 to n d over d theta 0, the logarithm of f of xi theta 0. And then I close the parenthesis here, just because here you have the joint density of x1, xn. And here what I recognize that I have simply the expectation of t of x1, xn multiplied by a quantity that is what? That is just the derivative, in fact, simply the derivative of the log likelihood. I have this one. So the derivative of the expectation is obtained as this one. We know that the derivative is equal to 1, so we have the following. I can write this, and it's almost finished, almost. We have obtained that d over d theta 0 of exponential expectation of t, excuse me, is equal to 1, and that this is equal to the expectation of t, okay, d over d theta 0 of ln of theta 0. Okay, so I have this one here. I just remark the following. I know, because I have already proved it, we know that the expectation of the derivative of the log likelihood, that is the expectation of the score, is necessarily equal to 0. It's a computation that I have done at least 2 times today. Okay, so the expectation of the derivative is equal to 0. And so what we have, I can say that if this is equal to 0, I can say that the expectation of t minus theta 0 multiplied by the derivative this one is equal to 1. Why I have this? Because from this one to this one, I have subtract by minus theta 0 the derivative, but I know that the expectation of this term, okay, so the expectation of this term, this single term is 0, so I can add the minus theta 0 or not, and will change nothing in my expectation here because I obtain 1, both guys, okay. You have the expectation of a difference, you write it as the difference of the expectation. The first term is 1, the second one is 0 from what I have said here. And now I can use Cauchy-Schwarz inequality now. I can use Cauchy-Schwarz inequality that will tell me that what I am interested in, that is these expectations here. So by Cauchy-Schwarz inequality, we have seen together Cauchy-Schwarz. You have here, if you want, x. You have here y. The expectation of xy, that is known to be equal to 1 by what I have done before, is less than the expectation of x squared to the power 1/2 expectation of y squared to the power 1/2. And what I obtain for this one, I obtain that, okay, simply that I can write it this way. The expectation of x squared is greater than 1 over the expectation of y squared. But what is the expectation of x squared here? It's just the mean square error of t, because it is the expectation of the square of this term, that is the mean square error, okay, because the expectation of the square is the variance in the case of an unbiased estimator, that is the mean square error. And here what I have, 1 over the expectation of y square. What is the expectation of y square? It's the expectation of the square of the derivative of the log likelihood. And here you have exactly by definition. So here just by definition, definition, the previous one, okay, which one? Okay, just let me know. On this one, it was definition B5. Definition B5 tell you that here you have 1 over I of theta 0. And in fact, I have done the proof of the Cramer-Rao inequality, okay, in this case, in the case where my theta is a scalar. So more important than the proof, okay, a proof that is just a nice application of the Cauchy-Schwarz inequality here. More than the proof, okay, what is interesting with this one is that you have, for an unbiased estimator in this situation here, the fact that you have a way to check if it is view, okay? If you have a mean square error that is equal to the inverse of the Fisher information, then you will be necessarily view. Okay, so it won't be necessary for you to do pairwise comparison with all the unbiased estimator of your parameter theta 0. If you check the fact that your mean square error is equal to the inverse of the information, necessarily you will have what you want, that is, okay, you will be view. Okay, so I have done the job in the scalar case, so just let me say a few words concerning the higher dimensional case, okay? That is, okay, this one, so not this one, so I remove this slide because I don't have used it, yeah. Okay, okay. So let's see what happened in the case where my parameter so what we have seen for the moment, okay, just and what we have proved, in fact, more than seen. So I have here, okay, theta 0 that belongs to, so what I have already done, okay? So when theta 0 belongs to R, okay, we have proved that if I have an estimator that is unbiased, then the mean square error of this estimator, that is the expectation of t minus theta 0 square, okay, that is its variance here, the variance of t, in fact, that is the mean square error, is greater than 1 over I0, I of theta 0, where I of theta 0 is the Fisher information matrix that was defined equivalently by this expression here. The second derivative with respect to theta of the log likelihood at the point theta 0. Okay, so it's the Cramer-Rao lower bound, okay, for theta belonging to R. Now I am interested in this case, the case where theta 0 belongs to R to the power D. Okay, meaning that my theta 0 is a vector. Okay, it's a vector with components, okay, that are, if you want, theta 0, 1 until theta 0, D. This is the vector theta 0 here. Okay, what is an unbiased estimator in this situation? In this situation, if you want, you have an estimator of such a quantity that can also be expressed this way. So you have a vector, in fact, with t scalar estimators. I can write t1, okay, of x1, x2, whatever, until td. To say that I am unbiased, okay, using what we have done concerning vectors, okay, just mean that unbiased in this situation just mean I can write it as in the scalar case that the expectation of t, that is a vector, is equal simply to this vector, theta 0. It is the meaning of being unbiased. Of course, now, okay, I can't consider the mean square error because the mean square error is a number representing the variance of my estimator. But in the case where I have a vector, okay, I have seen how to transform the notion of variance. The notion of variance was by the variance covariance matrix. Okay, so if you consider the analogous of the variance in a dimension higher than 1, it's what? It's this one, covariance between Ti and Tj. It's the variance covariance matrix. Of capital T. Okay, and of course, for d equal to 1, I recover the variance that is in my situation simply the mean square error. Okay, for the information matrix here, it will be very simple, okay, to extend it, and I extend it this way. Okay, so the analogous of this one, so this one is in dimension 1, okay, d equal to 1 here, and you can extend it this way. So instead of having minus the expectation of the second derivative, you will obtain a matrix of the partial second derivative, what we call the Hessian matrix of the log likelihood. So the information is defined this way as the Fisher information that is in fact now a matrix becomes from minus the expectation of the second derivative of the log likelihood minus the expectation of the Hessian matrix of the log likelihood. And of course, when d is equal to 1, I recover for this one, simply this one, because I have a single parameter. Okay. So the mean square error, I can substitute to the mean square error, that is the variance of T, the variance covariance matrix, and I can substitute to the information, the Fisher information, what we call the Fisher information matrix, obtained substituting to the second derivative of the log likelihood here, the Hessian matrix here, this one. Okay? And the Cramer-Rao inequality can be expressed this way, that the variance covariance matrix of T is always greater than the inverse. Now I have a matrix I theta 0 minus 1, the inverse of the Fisher information matrix that is defined this way. So just a little remark concerning this, just a little remark. So just a little remark. What is this inequality here? Because you have here a matrix and here also a matrix. What is the inequality between matrices? Because a priori you don't know what is the inequality between matrices. But here we have particular matrix. Because, okay, you work with symmetric matrix. Here you have the matrix of the partial derivative, and we know from Schwartz lemma that when I compute a second derivative, I can do it in the order I want. I first compute with the first variable and then with the second one. And if I do the converse, I will obtain exactly the same. Okay, so an Hessian matrix is a matrix that is symmetric. And of course, the variance covariance matrix is a matrix that is symmetric because the covariance between two matrices is equal to the covariance when I invert the order in the covariance definition. So we say the following. So what is the meaning? So when A and B are two symmetric matrices, what is the meaning of this one? The meaning of this one is, okay, we say that A is greater than B if and only if A minus B is positive. Okay, so in other words, A minus B is a positive symmetric matrix. And what is the meaning of this one? What is the meaning of being a positive symmetric matrix? Okay, but it's just that, well, it's a classical definition for symmetric matrix. Okay, it's positive matrix are ones with, in fact, positive eigenvalues. But in other words, I can also say the following, that for all, okay, so I have A minus B, that is a matrix of size, let's say here with my notation, n times n, okay. So, okay, so for all, okay, x1, xn, small x1, xn belonging to R to the power n. So here you have n line, 1 colon, okay, and I can denote it by small x. So for all x equal 1 xn belonging to R to the power n, okay, I have this one, x transpose A minus B x, that is positive, this one. So this is the meaning of being positive for two, yes, for being positive for a symmetric matrix, okay, from which I can deduce what is to be greater than someone if you are two symmetric matrix, okay, just simply that the difference is a positive matrix in this sense. So maybe more than enter into too much details, we are going to see an example we have already done together, okay. So let's do it maybe here, new page. So it's the case where x follows, so an example, n mu 0 sigma 0 square. So if you remind this, okay, it's something we have done together, so I don't remind when, okay, so it was here. It was here. Okay, in this case, so just let me remind you what we have done. It was in the first video concerning this. Okay, we have this. So it was this example, okay, where I don't know the mean and the variance of my Gaussian. I can compute the log likelihood this way, and I can also compute the derivative of the log likelihood in this situation, okay? And I obtain this one. We are going to see what happened in this situation, so from which I have deduced that the maximum likelihood estimator in this situation was, okay, for the mean, the sample mean, and for the variance, the sample variance, okay? So we are going to see in this situation, okay, what happened for the Cramer-Rao inequality. So what happened for the Cramer-Rao inequality in this situation, okay? So keep in mind that my theta 0 here is equal to mu 0 sigma 0 square. And the fact that we have already seen together that if I compute the derivative of the log likelihood here, with respect to theta, I have obtained what? So it's a vector here because I have the derivative with respect to the first, that was my mu, and the second, that is the derivative with respect to sigma square. Okay, I obtained this one. So I have already done the computation. So I just write it, okay, sum from I equal to 1 to n, x I minus mu over sigma square. And here I have obtained minus n over 2 sigma square plus the sum from I equal to 1 to n of xi minus mu square over 2 sigma 4. Okay, so keep in mind I obtain from the log likelihood and its derivative, that is I have called the score function here. So you have the derivative with respect to mu and the derivative with respect to sigma square. I obtain this one, from which I deduce that, okay, I have mu hat in this situation that is equal to the sample mean, and I have sigma square hat that is the sample variance here. That is just the sample variance, okay? That is sigma n hat square. Here, it's the sample mean here. So if I compute the Hessian matrix of this one, okay, so the Hessian matrix of the log likelihood mu sigma square, I obtain the following matrix. So here you have the derivative with respect to mu. If I compute the second derivative with respect to mu, I obtain what? If I obtain the second, I compute the second derivative with respect to mu, I obtain minus n over sigma square. It's the derivative of this one with respect to mu, because I obtain here minus 1, n time because I have n term in my sums, okay, over sigma square, that is exactly this one. If I compute the derivative of this one with respect to sigma square, with respect to sigma square, so it's like I have 1 over x, I compute the derivative, it's minus 1 over x squared, so I obtain for the derivative of this one with respect to sigma square, the sum from I equal to 1 to n xi minus mu, with a minus before, and divided by sigma square, that is sigma 4 here. That is the derivative of this one with respect to sigma square. I obtain here a constant, that is the sum, 1 over sigma square, that becomes minus 1 sigma 4 if I compute the derivative. For the derivative of this one with respect to mu, I obtain minus the sum xi minus mu over sigma 4. And it remains this term here that will be the derivative of this one with respect to sigma square. Maybe just I will enlarge a little my matrix here. I have a matrix of size 2, 2 here. It's the Hessian matrix here, this one. And here, if I compute the derivative of this one with respect to sigma square, I obtain what? I obtain n over 2 sigma 4. And for this one, plus the sum from I equal to 1 to n of xi minus mu square over what? Over, okay, so I have the over 2 here. Okay, and I obtain minus 2 multiplied by, I have sigma to the power 6 here, because sigma 4 may be written as 1 over x squared with x equal to sigma square. Okay, and I obtain here multiplied by minus 2. So it's important to do this computation by yourself at home. It's just computation of derivatives. The only thing you have to be careful with, okay, is that here you compute the derivative with respect to mu, so no problem. And the other derivative is with respect to sigma square, not the derivative with respect to sigma. Sigma square is the parameter of interest. So if you are not fluent with this kind of derivation, just write, okay, give a name to sigma square, call it small x if you want, okay, and then you apply the classical formula you know concerning derivative. That's why here, okay, I obtain minus 2 over sigma to the power 6, because the derivative of 1 over sigma 4 with respect to sigma square is minus 2 over sigma to the power 6, as the derivatives of 1 over x squared is just, okay, 1 over x squared is minus 2 over x to the power 3. Okay, exactly, to obtain this one. Okay, so we obtain this quantity, and I see that, okay, so let's duplicate this slide here. So if I erase the previous computation. So I erase this one, this one, this one. And I am interested so in the Hessian matrix. You know that the Fisher information is just minus the expectation of the Hessian matrix at the point theta 0, where theta 0 here, keep in mind that my theta 0 is mu 0 sigma 0 square. Okay, I have this one. And so when I compute the expectation of this one, but it won't be that complicated, in fact. So it's minus, okay, because I minus the expectation of this term. So I have to compute minus the expectation of each term of this matrix here, okay? So here, it's a constant, so minus this constant is just n over sigma square here. Here, if I compute the expectation, by the expectation of all this term here is 0, so I obtain 0. The same hold here, because the expectation of this one is 0. So I have a matrix that will be, in fact, a matrix that is diagonal in this situation. And here, if I compute the expectation of this term here, so here I have my constant, okay, minus the expectation. Here I have my constant, and here I know that each expectation here is equal to sigma square. And so you can see easily that this term is just n over 2. So I have sigma 0 here, 2 sigma 0, 4. And so if I compute the Fisher information matrix here, that is this one, it's inverse. But since I have a diagonal matrix here, computing the inverse is not that complicated. Sigma 0 square, okay, over n, 0, 0, 2 sigma 0, 4 over n. Okay, so you have the inverse of the information matrix that give you this one. Okay, so I have this one. Okay, so if I come back to my problem here, so I duplicate once again, okay, to obtain this one, I erase this one, and I have your information matrix here. So what the Cramer law Loberbaum tell me is that the variance covariance matrix of an estimator. So if I have an estimator, excuse me, if I have an estimator here, let's call it, okay, capital T, that is T1, T2 here. Okay, an estimator of mu 0 and sigma 0 square. Okay, so I call it this one. I have the variance covariance matrix, so I suppose it to be unbiased. That is the expectation of T. Okay, let's write it to be equal to, if I write it this way, okay, is equal to mu 0 sigma 0 square. Why not? Okay, I have something that is unbiased. Okay, so if I write the Fisher information matrix, the variance covariance matrix of this one, okay, that is what? Okay, I can write it this way. It's the expectation of T1 minus mu 0 square. Here I have expectation of T2 minus sigma 0 square. So let me, it's not clear that way. I will write it in a bigger way. Okay, so the Cramer-Rao inequality written in this framework tell me that here I have what? I have the expectation of T1 minus mu 0 square in the first term of the diagonal. Here, expectation of T2 minus sigma 0 square here. And here I have the covariance. Okay, so write it this way with a star. Okay, where star is simply equal to, okay, the expectation of T1 minus mu 0, T2 minus sigma 0 square. I have this one, and the Cramer inequality tell you that here, this matrix considered as the symmetric matrix is greater than the inverse of the Fisher information that I have found to be this one. Sigma 0 square over n, 0, 0 to sigma 0, 4 over n. Okay? And in particular, from this, but I know that this one has to be greater than this one, and that this one has to be greater than this one, okay, because of, okay, what I can deduce from the inequality between positive matrix. But what we have seen together? We have seen together that, let's write it this way. We have seen together that mu hat in this situation was the sample mean in the situation here, with a variance that I am able to compute. That was equal to sigma 0 square over n. If I come back to what I have said previously, here, from the first term in the diagonal of my inverse matrix, I see that, okay, I obtain exactly sigma 0 square over n. Okay, I obtain exactly sigma 0 square over n. That is my variance here, implying that in this situation, sigma over line is mu, best unbiased estimator. I have also seen that sigma square hat is just the sample variance here with a variance that I have previously computed just at the end of the first video, okay? So I have something that is biased, okay, for sure, with, so I have something, let's say, that is biased here. So you have here, in the case of the variance of a Gaussian with the two parameters that are unknown, okay, what you obtain as the maximum likelihood estimator for the variance is something that is biased, okay? So you can say nothing for this one because it is a biased one, okay? Concerning this one, I know that I can make it unbiased if I consider the corrected sample variance. This one is unbiased. And at the end of the first video concerning the estimation, I have shown you how to compute this one. This one was this quantity here, this quantity, because of a result we have seen at the beginning of the first video and also in the previous chapter. And I see that this one that is unbiased of sigma square, but it is not BU, in fact, in my situation. Why it is not BU? But it is not BU, it's not the best unbiased estimator because when I come back to my previous computation, the second term in the diagonal of the Fisher information, the inverse of the Fisher information matrix, is equal to this quantity, and the variance of my corrected sample variance is not equal to this one. So I can write it this way. This one here is strictly greater than 2 sigma 0 square over n, C I0 minus 1 theta 0. Okay, so I can write it this way also, 0 sigma 0 square over n, C I minus 1 of theta 0. And it implies that if the sample variance is BU, Sn square is not BU. Okay. So you will see that for the slides, I have in the slides, okay, 2 last pages that I will consider as out of the program for the final exam. I have already done enough things for estimations, okay? So it concerns Bayesian estimation. Maybe if I have time, I will record you a little video on this topic, okay? But it is in all the cases out of the program of the final exam, okay? So if I want to summarize what we have seen today, so I have done a lot of proofs in this session, okay? And I have also done some examples. So for the proof, you can omit them if you want, okay, for the final exam. It's not that important. What I want you to keep in mind in this session is I want you to be able to find a maximum likelihood estimator, okay, in general. And how to do this? You compute the log likelihood in the discrete or in the continuous case, and then you have to solve a single or 2 or 3, depending on the size of your problem, okay, Euler equation in order to obtain the maximum likelihood estimator. So I want you to be able to do this, okay? And you will see that in the tutorial, we are going to do this several times, okay? And once we have obtained maximum likelihood estimators, our question is, are they optimal? Okay, so are they best unbiased estimator? And to do this, okay, we can answer easily this question by seeing if the mean square error related to an unbiased estimator, and namely here, maybe the maximum likelihood estimator when it is unbiased, reach or not the lower bound of the Cramer-Rao inequality. And in order to check this, you have to be able to compute the information or the information matrix, okay, as we have seen today, to compute the inverse of this number or the inverse of this matrix, and to check if your estimator of interest reach this lower bound or not. Okay, so solve Euler condition for the log likelihood will allow you to obtain maximum likelihood estimator. Compute information or information matrix, okay, will give you the lower bound in the Cramer-Rao inequality to check if you reach or not the Cramer-Rao lower bound. In the case where you reach, you will be able to deduce that you have a best unbiased estimator. So in this session, with respect to what we have done in the previous one, okay, I have obtained a general way in order to obtain an estimator of a quantity of interest, okay, through the maximum likelihood estimator, and with the criteria in order to check, okay, if it may be optimal or not. So you will see that I will practice all these notions in the tutorial that will arrive, okay, in the next video. Okay, so I repeat just the last time that for the final exam, okay, you don't have Bayesian estimation. That are the 2 last slides of my slides that I don't want to deal with for this year, okay, and also that don't spend too much time on the proofs, okay. Have a look on the definition of the theorem, okay, and then have a look on the examples we have done together in class and on the exercise we are going to do together in the tutorial. So see you, bye-bye. Bye-bye.